Hi, today is we're going to be doing Codeforces around 856 Div 2 Problem D. I'm going to just read the question, read the editorial, and try to read someone's code and then try to code it up. This is the problem I had some ideas, but I didn't get entirely in contest. Okay, so the problem, which is on the screen now, is the prime. So maybe I could explain this problem here. I will share desktop too. Okay. Code in this. And the problem is as follows. Let me explain the code, the problem. You are given a multiset, for instance, let's say 2, 3, 3, 1, right? And we know, okay, you're given, so this is your input, you're just given this multiset. So what we need to do is arrange numbers in this in the form of P1 to the E1, P2 to the E2, which will end up giving us some number, say X. And the number of different X's we can get for different arrangements of numbers in this multiset is what we need to display, right? And these guys can be any integers, not necessarily prime. And this is the prime factorization, by the way. P are primes and E are their exponents. Okay. So we have been given 2n integers. Yeah. So I guess immediately you see that there can only be primes at the bottom, and the rest of the primes and non-primes are in the exponent. And at the bottom, you can't have, like, for instance, 3, 3. You can't have P1 equals 3 and P2 equals 3. That, like, for prime factorization, you only have like unique numbers, right? So that's not allowed. Yep. So you have to count all possible ways to do this. So I guess the idea I was thinking about last time was if you fix, so say you have, let's say integer n1 occurs k1 times, okay, let's not call this n1, let's call this x1 occurs k1 times, x2 occurs k2 times, and so on, x, right? And let's say, so these, let these be the, or let me call these P1 occurs k1 times P2. So these are the primes. And then you have the non-primes, say x 1 occurs q1 times and x2 occurs q2 times, and so on, right? So primes and non-primes. Once you pick the primes, how many different arrangements do you have for the rest, right? So you have n numbers for the exponents remaining. So there's n factorial ways to arrange those, okay? And that you divide by, obviously the non-primes are all on the top. So you obviously have q1 factorial, q2 factorial. These are the number of occurrences for each x1, x2, and so on for the non-primes. For the primes, the thing is, the ones that you have selected in this current arrangement, so let's say for some arrangement X, in this current arrangement, the primes you have selected, those guys, you will have k1 minus 1 like for those guys, you'll have k1 minus 1 factorial because you've selected there's only k1 minus 1 of them. And for the ones you haven't selected, it'll be like k2 factorial. So this is what you need to be counting for every single arrangement, okay? Now, the idea was, okay, that this is a lot of counting to do. Is there any way we can store something and like potentially compute this? So I guess the um I guess the idea was to start thinking in which of these terms you have a k1 minus 1 factorial and which of these terms you have a k2. Like you have it without the minus 1, right? And like, I mean, this isn't like, I mean, this is because I've seen other DP problems is what I'm thinking this way. It's not like I'm looking at this and directly thinking what I'm about to say next. But maybe we can think about for a given, okay, how do we think? Uh, okay, first thing is these Q1 factorial, Q2 factorial guys will take up some space. So all the non-primes will take up some space. So whatever is left is the primes. Okay, let's call the remaining slots as M. There's probably M slots. There are M slots left, right? And those total M slots are in which you have primes. Now, let's say okay, let's assume that, and I know I'm putting a lot of variables here. I think I'll have to clean this up. Um, let's assume till okay, at say the rth prime. Okay, say we know how to arrange r minus the previous r minus 1 primes um, in up to m minus, okay, not m minus kr, I don't know, in m prime slots where m prime is k1 plus k2 and so on up to kr, right? So screw this n factorial by thing. This is always going to be there for everything. Um, so I claim that the, like dp of the rth prime in m slots I'm thinking in some complicated way. Okay, maybe this part is complicating it. Okay, let's just say that we're going to this part m plus 1 into m plus 2 and so on up to n by q1 factorial, q2 factorial. That part we'll add in the end, we'll multiply in the end with whatever we get. So now we are left with just how to arrange these primes. That's it. So we are left with m factorial by whatever. K1 minus 1 factorial. K2 factorial and so on based on the arrangement and sum over all of the arrangements. Which okay, say we just had one prime p1 Then the solution would be k1 factorial by k1 factorial. Um, yeah, no. Yeah, and I feel like I'm not thinking about this properly, so I will read the editorial. Yeah, I feel this much is fine. Hmm. So this is checking prime, and we're doing it in square root of n, 10 to the 6. N can be up to 10 to the 6. So that's 10 cubed for 1,000 numbers. That's not nice. Or is that okay, apparently? 10 to the 6 is usually the limit, no? 10 to the 6. Okay, apparently this works. Exponent, that's fine. I was thinking of to use a map, but they just used a vector pair. Completely forgot about pairs. Oh my god. We'll have to see what this F does. Okay. A contains the input. They've sorted the input. I wonder why. Oh, oh, nice. Acom, what is dot back dot first? I guess dot back is the last element. Dot first is the first in the pair. Nice. I like this compressed list. Yeah, that's super smart. I wouldn't have done it this way. I wouldn't have sorted and compressed. I guess what I would have done is made a map and yeah, input it in there, which I guess both are okay. They're just computing all of the factorials all the way up till max n. And they aren't even like they've fixed, oh, max n is like double. They're computing it for everything, not just the input. A bunch of things I wouldn't have done, I guess, like computing factorials and keeping them. That is smart, I think. DP was initialized right here. I actually don't know the syntax of memset. Oh, the FDP part is in F. I don't understand LL and res equal 3px, comma. What? They're doing a recursion DPO. Why are they doing that? Is that easier to think about? I don't know. It seems like it's much easier to do it iteratively. Why are they recursing? Hmm. Yeah, so why are they recursing? Like, what are they? First of all, what does this mean? I keep getting confused with these address nonsense. Yeah, I'm not gonna have time to code this up, but we'll do before. Publishing. X is the last guy. Res equals Y equals 0. I believe this returns res as well as sets res equal to this. Y equals 0 is just 0 or 1. I see. They are 0, comma. What to Yeah, what does it mean to say return A equals something? Does it return this and set this to be equal? Which is weird. I guess it has something to do with the and here. Yeah, I'm confused. Yeah, I definitely wouldn't have used dot back. Mindset syntax. Find it. So yeah. So I think one like sort of um thing that I realized I was getting confused with is I know that I had to do n factorial by all those q1 factorial, q2 factorial, which were the non-primes. And then for each of the primes, I had like I think they wrote it best k1 factorial, k2 prime factorial, and so on, kn, k, let's say x prime factorial. Um, Sum over each ki is equal to ki and ki minus 1, right? Minus 1. So all I needed to do was, let's say, g of x comma y is the above product. No, g of x comma y is 1 by k I k1 prime sum k I is ki prime is equal to ki comma ki minus 1 ki over all this, so k1 prime factorial, k2 prime factorial, and so on up to kx prime factorial. And then I know that g, oh sorry, not all possible minus ones. Somewhere with y negative signs. I guess it's not the best way of writing it, but yeah, y negative signs. So now I know g of x comma y. If you want to add the x element with y negative signs, it's equal to 1 by kx factorial into g of the x minus 1th element with y negative signs plus 1 by kx minus 1 factorial into the x minus 1th element with y minus 1 negative signs. So basically, I didn't have to think about the choosing elements and what's going on in that whole thing. I didn't have to worry about the whole formula. Since in the final step, I only need to know that I need to sum this up over y negative signs, I could have just done this. So I guess that part I missed out. I will code this up and post, but yeah, right now no code in this video. Thank you for watching, if at all anyone watched. I don't think you get much out of this particular video.